Right now, as you listen to this, 95% of the universe is made of something we've never seen, never touched, and don't understand. And that's just the beginning. Welcome to the greatest unsolved mysteries in all of science. Tonight, we're going to explore 100 questions that keep scientists awake at night. Not because they're hard, but because they might be impossible. These aren't small puzzles. These are cracks in our understanding of reality itself. Questions so fundamental that answering even one of them could rewrite everything we think we know. So get comfortable, maybe dim the lights, let your mind wander into the unknown. Because for the next hour, we're going to journey through the deepest mysteries of existence and discover that not knowing can be just as beautiful as knowing. Let's start with the biggest question of all. Why does anything exist? Not how. Why? Why should there be a universe at all, instead of just nothing? Think about that for a moment. Nothing is simpler than something. Emptiness requires no explanation, no laws, no forces, no beginning or end, just eternal, perfect nothingness. And yet, here we are, stars burning, planets spinning, you thinking about your own existence. Science can trace the universe back to the Big Bang. We can describe how atoms formed, how galaxies evolved, how life emerged, but we can't answer why any of it should exist in the first place. Some physicists say the universe might be a quantum fluctuation, that nothingness is actually unstable and something must inevitably pop into existence. But that just pushes the question back. Why should quantum mechanics exist? Why should there be laws that allow fluctuations at all? Others suggest we live in a multiverse, with infinite universes bubbling into existence. But again, why should there be a multiverse-generating mechanism instead of nothing? The question sits at the foundation of everything. Every scientific discovery, every equation, every observation, all of it assumes existence. None of it explains why. We know the universe began. We don't know what made it begin. 14 billion years ago, everything that exists was compressed into a point smaller than an atom. Then, in an instant, space itself exploded outward faster than light. We call it the Big Bang, but what banged? Cosmologists can describe what happened a fraction of a second after the beginning. They can trace the formation of the first atoms, the birth of the first stars, but the moment of creation itself, that's hidden. Some theories imagine a quantum spark. Others propose colliding membranes in higher dimensions. Some suggest the Big Bang wasn't the beginning at all, but just one cycle in an eternal process of birth and death. The problem is that time itself began with the Big Bang. Asking what came before might be like asking what's north of the North Pole. The question might not even make sense. And yet we can't help asking it, because something set this whole cosmic story in motion. Something started the clock. Something created time, space, matter, and energy from what? Time flows forward, always forward, never backward. You remember yesterday, but not tomorrow. A glass shatters, but never unshatters. Heat spreads, but never spontaneously concentrates. Entropy always increases. This is called the arrow of time, and it's one of the strangest features of reality. Here's the weird part. The fundamental laws of physics don't care which direction time flows. Newton's laws work just as well backward as forward. Einstein's equations are time-symmetric. Even quantum mechanics allows processes to run in reverse. So why does time only flow one way in our everyday experience? Scientists usually point to entropy, the tendency toward disorder. The universe started in a highly ordered state and has been getting messier ever since. We experience time flowing toward greater disorder. But this just raises another question. Why did the universe start so ordered? Why was the Big Bang a state of low entropy rather than high entropy? No one knows. Time is something we live inside every moment. It carries us from birth to death. It's so fundamental we can't imagine existence without it, and yet we don't understand why it flows the way it does.
Most of the universe is invisible. When astronomers measure how galaxies rotate, something's wrong. The outer edges spin too fast. By all the laws of physics we know, those stars should fly off into space like water off a spinning wheel. But they don't. They stay bound, which means there must be extra mass we can't see. Lots of it. We call it dark matter. It makes up about 85% of all matter in the universe. It's everywhere, passing through you right now, but we've never detected a single particle of it. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with normal matter except through gravity. It's like a ghost that only reveals itself by how it pulls on things. Scientists have searched for dark matter particles for decades. They've built detectors deep underground to shield them from cosmic rays. They've looked for signals from space. They've tried to create dark matter in particle accelerators. Nothing. We know it's there because we can see its gravitational effects. Galaxies are embedded in huge halos of dark matter. The cosmic web, the large-scale structure of the universe, is held together by it. But what is it? Some new kind of particle? A modification of gravity we don't understand? Something even stranger? 5 times more abundant than normal matter, and we don't know what it is. If dark matter is strange, dark energy is stranger. In the 1990s, astronomers discovered something shocking. The universe isn't just expanding, it's accelerating. The expansion is speeding up. This should be impossible. Gravity should be slowing the expansion down, pulling galaxies back together. Instead, some mysterious force is pushing them apart faster and faster. We call it dark energy, and it makes up 70% of everything that exists. 70%. The vast majority of the universe is this invisible, repulsive energy that we don't understand at all. One idea is that it's a property of space itself. Empty space might have inherent energy that causes expansion. Einstein actually predicted this with his cosmological constant, though he later called it his biggest blunder. Another possibility is that dark energy is dynamic, changing over time. Maybe it's a new field pervading space, something we've never encountered before. Or maybe our understanding of gravity breaks down on cosmic scales. Maybe Einstein's equations need correction for the largest distances. Whatever it is, dark energy will determine the ultimate fate of the universe. If it stays constant, galaxies will drift apart until only darkness remains. If it grows stronger, it could eventually tear apart stars, planets, even atoms. We can measure its effects. We cannot explain what it is. The universe seems designed for life, and we don't know why. The laws of physics depend on certain constants: the strength of gravity, the charge of an electron, the mass of the Higgs boson. These numbers could, in principle, be anything. But if they were even slightly different, life would be impossible. If gravity were a tiny bit stronger, stars would burn out too quickly for life to evolve. If it were weaker, stars might never form at all. If the electromagnetic force were different by 1 part in a billion, carbon, the basis of all life we know, couldn't exist. If the strong nuclear force were 5% weaker, the only element in the universe would be hydrogen. No chemistry, no planets, no us. The universe sits on a knife's edge. Change almost any fundamental constant by a hair, and you get a sterile cosmos. No complexity, no consciousness, just empty space, or perhaps just hydrogen gas. This is the fine-tuning problem. Why are the laws of nature set to exactly the values that allow life? Some say it's coincidence. Others argue it's proof of a multiverse, infinite universes with different constants, and we just happen to live in one where life is possible. Others see it as evidence of design, though that raises its own questions. The universe appears uncannily suited for our existence, and we don't know whether that's meaningful or just the way things are. We can see about 93 billion light-years in every direction, but we don't know if that's all there is. The observable universe might be just a tiny bubble in something infinitely larger, or it might be finite but unbounded, like the surface of a sphere, where traveling far enough in one direction brings you back to where you started. Current measurements suggest the universe is flat, or very nearly so. But flat doesn't tell us if it's infinite. If it is infinite, then somewhere out there, far beyond what we can see, there might be another you. In fact, there might be infinite versions of you living infinite variations of your life. This isn't science fiction, it's a genuine consequence of an infinite universe. With infinite space and infinite matter, every possible arrangement must occur somewhere. Not just once, but infinitely many times. Or maybe the universe is finite. Maybe if you could travel far enough, you'd reach what? An edge? A boundary? The observable universe is like standing in fog. We can see a certain distance, and then our view is blocked. What lies beyond the fog, we simply cannot know from here.
Even stranger, most of the universe is accelerating away from us so fast that we'll never reach it. Because of dark energy, distant galaxies are receding faster than light, not because they're moving through space that fast, but because space itself is expanding. This creates a boundary. Beyond a certain distance, light from those galaxies will never reach us. They're not just far away, they're unreachable in principle. As the universe continues to expand, more and more galaxies will cross this boundary. In trillions of years, alien civilizations in our galaxy will look up at a sky almost empty of other galaxies. They'll see only the local cluster. They might conclude they live in a small, lonely universe. They'd have no way of knowing about the vast cosmos beyond their reach. This raises an unsettling question. What are we missing right now? What lies beyond our cosmic horizon that we can never see or know about? The universe we can study might be an infinitesimally small fraction of what actually exists. Our universe might be one bubble in an infinite foam. Several theories in physics predict multiple universes, not just similar to ours, but fundamentally different. Inflation theory suggests that the rapid expansion after the Big Bang might create countless bubble universes, each with potentially different physics. String theory predicts a vast landscape of possible universes, maybe 10 to the 500 different configurations, each representing a unique set of physical laws. Quantum mechanics, in some interpretations, suggests the universe splits every time a quantum measurement occurs, creating parallel worlds for every possible outcome. If any of this is true, then reality is far vaster than we imagined. Our universe, with all its galaxies, all its mysteries, might be just one note in an infinite cosmic symphony. But here's the problem. How do you test this? If other universes are forever beyond our reach, can we ever know they exist? Is the multiverse even science, or is it philosophy? Some physicists embrace it as the best explanation for fine-tuning and other puzzles. Others reject it as unfalsifiable speculation. The multiverse might be the answer to everything, or it might be a beautiful idea that can never be proven or disproven. Space and time might not be fundamental. We think of space-time as the stage on which the universe plays out. But what if the stage itself emerges from something deeper? At the smallest scales, far smaller than atoms, smaller than quarks, space-time might break down entirely. It might become grainy or fuzzy or dissolve into something we don't have words for. Some theories suggest space-time emerges from quantum entanglement, the strange connection between particles. In this view, space and time aren't fundamental, they're patterns in a deeper quantum reality. Others propose that reality at its deepest level is information, and space-time is just how we perceive the flow and processing of that information. If they're right, then asking what space-time is made of is like asking what computation is made of. It's not made of anything. It's a process, not a substance. We live inside space-time. We measure distances in it, track durations with it. It feels as real as anything can be. And yet, it might be an illusion, a useful description that breaks down when you look too closely. A particle can be in multiple places at once, and no one knows what that really means. In the quantum world, particles don't have definite positions until you measure them. Before measurement, they exist in a superposition, a ghostly combination of all possible locations. This has been proven thousands of times. Electrons pass through two slits simultaneously. Atoms exist in multiple energy states at once. Molecules can be made to be in two places, separated by distances visible to the naked eye. But what does it mean for something to be in two places at once? Is the particle really, physically, in both locations? Or is superposition just our ignorance? We don't know where it is until we look. Some interpretations say reality itself is indefinite until observed. Others claim reality splits into parallel universes for each possibility. Still others argue there's a deeper level of reality we're missing. The math works perfectly. The predictions are astoundingly accurate. But a century after quantum mechanics was discovered, we still don't know what it's telling us about the nature of reality. Two particles can be connected across any distance instantaneously. When particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Change the spin of one, and the other changes immediately. Not after light has time to travel between them, immediately. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But every experiment confirms it's real. Entanglement doesn't allow faster-than-light communication. The changes are random, so you can't send information, but it reveals something profound about reality. The universe seems to be non-local. What happens here can instantaneously influence what happens there across light years of space, as if distance, at some fundamental level, doesn't exist. Some physicists think entanglement hints at hidden dimensions or reveals that space is an emergent phenomenon. Others see it as proof that the universe is fundamentally holistic, with everything connected to everything else. We use entanglement in quantum computers and encryption, but we don't understand why it works. Why should reality be woven together in this impossible way?
Observing something changes it, and we don't know why. In quantum mechanics, particles exist in superposition until measured. Then they collapse into a definite state. But what counts as measurement? What triggers the collapse? Is it consciousness? Does a particle need to be observed by a thinking being to become real? Is it interaction with a large object? Does a particle collapse when it hits a detector? Or does the detector enter superposition too? Some interpretations say collapse is real. Something physically happens when you measure. Others deny collapse happens at all, saying all possibilities continue to exist in parallel universes. Still others claim the wave function is just information, and collapse is simply updating your knowledge, not changing physical reality.
This isn't just philosophical. The measurement problem touches on the nature of reality itself. Are things definite when we're not looking? Or does observation somehow bring reality into being? We can calculate what will happen when we measure. We cannot say what measurement actually is. Gravity is trillions of times weaker than the other forces, and no one knows why. A tiny magnet can pick up a paperclip, overcoming the gravitational pull of the entire Earth. Electromagnetic force is vastly stronger than gravity. The strong nuclear force is even more powerful. If gravity were as strong as the strong force, a person would generate a black hole. This hierarchy problem is one of physics's deepest mysteries. Why is gravity so pathetically weak? One idea, gravity spreads into extra dimensions we can't see, diluting its strength in our three-dimensional space. Another, the Higgs field, which gives particles mass, might be unnaturally light, and this somehow weakens gravity. Or maybe there's a deep symmetry in nature we haven't discovered that requires gravity to be weak. Without gravity's weakness, stars couldn't form. Planets couldn't exist. Life would be impossible. We wouldn't be here to wonder about it. The weakness of gravity seems arbitrary, yet everything depends on it. Our two best theories contradict each other. General relativity describes gravity beautifully. It's been tested countless times and always proven right. Black holes, gravitational waves, the expansion of the universe, all predicted by Einstein's equations. Quantum mechanics describes the microscopic world with incredible precision. Every electronic device you use depends on it. It's been tested trillions of times and never failed. But they contradict each other. When you try to apply quantum mechanics to gravity, you get nonsense, infinite probabilities, equations that break down, predictions that make no sense. At the heart of a black hole, or in the first instant of the Big Bang, both gravity and quantum effects matter, but we have no theory that handles both. String theory tries to unite them. Loop quantum gravity takes a different approach. Other theories propose even stranger solutions. None have been confirmed. We're still searching for the theory of everything, the framework that can describe reality at every scale. Until we find it, we're working with two incomplete pictures, each perfect in its domain, both failing when pushed to extremes. At the center of every black hole is a point where physics breaks down. According to Einstein's equations, all the matter that falls into a black hole gets crushed into an infinitely dense point, a singularity. But infinity is usually a sign that your equations have failed. What's really at the center of a black hole? Some think quantum gravity will replace the singularity with something finite. Others imagine a bounce where infalling matter rebounds into a new universe. We cannot observe what happens inside. The event horizon shields the singularity from view. Whatever mysteries lie at the heart of black holes are hidden forever. Or are they? Some theories suggest black holes might have naked singularities, singularities not hidden by horizons. If those exist, we could study them directly. For now, singularities remain where our knowledge ends. They're boundaries of scientific understanding, places where the equations point but cannot enter. When matter falls into a black hole, information might be destroyed, which should be impossible. Physics has a basic principle. Information is never truly lost. If you burn a book, the information isn't destroyed, it's encoded in the smoke, heat, and ash. You could, in principle, reconstruct the book. But black holes seem to violate this. When something crosses the event horizon, it's gone. And if the black hole evaporates through Hawking radiation, where did the information go? If it's destroyed, quantum mechanics is wrong. If it escapes, we don't know how. The radiation seems to carry no information about what fell in. Stephen Hawking wrestled with this for decades. Some physicists now think information is stored on the event horizon itself, encoded in subtle patterns. Others propose black holes don't truly evaporate, but leave remnants containing the information. Still others suggest our understanding of time breaks down near black holes, and information isn't actually lost from a certain perspective. The paradox remains unsolved, touching on the deepest laws of physics.
Black holes should glow, but we've never seen it. Quantum mechanics predicts that black holes emit radiation, very faint, very slowly, but real. Over unimaginable timescales, this radiation would cause black holes to evaporate completely. This prediction ties together quantum mechanics, relativity, and thermodynamics in a beautiful way, but it's never been observed. Real black holes are far too hot from infalling matter to detect the tiny trickle of Hawking radiation. We'd need an isolated, quiet black hole, which doesn't exist in our observations. Lab experiments have created analogs using sound waves and fluids, and they seem to confirm Hawking's prediction. But it's not the same as seeing actual black holes glow. If Hawking radiation is real, it means black holes aren't eternal. Even the largest will eventually fade away, leaving only cold, empty space. Until we detect it directly, Hawking radiation remains one of the most important unconfirmed predictions in physics. Black holes might connect to other regions of space-time. The mathematics of Einstein's equations allows for wormholes, tunnels through space-time connecting distant regions or even different universes. Some solutions suggest black holes could be entrances to these tunnels. Fall into a black hole, and you might emerge elsewhere. Of course, you'd be destroyed by tidal forces first. The journey would be one-way and fatal, but the mathematical possibility exists. Other theories propose black holes create new universes. The matter crushed at the singularity might undergo a quantum bounce, spawning a new space-time on the other side. If true, our universe might have been born from a black hole in another universe, and every black hole in our cosmos might be creating new universes. These ideas are speculative, but grounded in real physics. They push the boundaries of what black holes might be, not just cosmic vacuum cleaners, but gateways to elsewhere. We've never seen the very first stars. After the Big Bang, the universe was dark for hundreds of millions of years. No stars, no galaxies, just clouds of hydrogen drifting in the void. Then, the first stars ignited. They would have been massive, hundreds of times the mass of our sun, burning intensely but briefly before exploding as supernovae. These population 3 stars forged the first heavy elements, seeding the cosmos with carbon, oxygen, iron. They made everything that followed possible. But we've never observed one. They lived and died so long ago, so far away, that their light hasn't reached us in any form we can detect yet. The James Webb Telescope is searching for their signatures. We might finally glimpse the universe's first light. Until then, the first chapter of cosmic history remains unread. Some black holes grew too big, too fast. At the center of most galaxies lurks a supermassive black hole. Ours weighs 4 million times the sun. Some are billions of times more massive.
The puzzle: we see these giants less than 1 billion years after the Big Bang. They shouldn't have had time to grow so large. Black holes grow by swallowing matter, but there's a limit to how fast they can feed, the Eddington limit. Matter falling in heats up and radiates, creating pressure that pushes away more matter. Even feeding at maximum speed continuously, black holes shouldn't reach billions of solar masses in under 1 billion years. Did they form from the direct collapse of giant gas clouds, skipping the star phase entirely? Did they somehow exceed the Eddington limit? Did they grow through mergers faster than we think possible? Each explanation has problems. The rapid growth of supermassive black holes challenges our understanding of how structures form in the universe. Spiral galaxies shouldn't stay spiral. The Milky Way's beautiful spiral arms should wrap up and disappear. Galaxies rotate, but not like solid disks. Inner parts spin faster than outer parts. After a few rotations, spiral arms should wind up completely. Yet spirals persist for billions of years. The leading explanation: spiral arms are density waves, not fixed structures. Stars and gas move through the arms like cars through a traffic jam. The arms themselves don't rotate like rigid spokes. But this raises questions. What maintains the density waves? Why are they so common? Why do some galaxies have 2 arms, others 4? Computer simulations can create spirals, but often they're messier than real galaxies. Something about galactic dynamics produces elegant, long-lasting spirals, and we don't fully understand what.
Mysterious blasts of radio waves flash across the universe. Fast radio bursts last milliseconds and release energy equivalent to the sun's output over decades. We've detected thousands coming from all directions in space. Some repeat, others don't. Some come from identifiable galaxies, others from empty space. What causes them? Magnetars, neutron stars with extreme magnetic fields, are the leading candidate, but not all FRBs match that profile. Could some be from colliding neutron stars, black hole events, something even more exotic? Every so often, one of these bursts appears in our telescopes, a fleeting flash from billions of light years away, gone almost as soon as it arrives. They're probably natural phenomena, but their power and mystery have led to speculation about alien technology. A civilization beaming energy across space might create signals like this. Most likely, FRBs are teaching us about extreme physics we've never encountered, but until we pin down their source, they remain cosmic question marks. Something massive is pulling our galaxy. The Milky Way, along with thousands of other galaxies, is moving toward a region of space at hundreds of kilometers per second. This motion isn't from the universe's expansion, it's additional, extra movement. Something huge must be pulling us. We call it the Great Attractor. It's partially hidden behind the plane of our galaxy, shrouded in dust and stars, making it difficult to observe directly. Mapping reveals a massive supercluster of galaxies in that direction, but even that might not be the full story. Beyond it lies the Shapley supercluster, even more massive. Our galaxy is falling toward something we can't fully see, pulled by gravity from unimaginable concentrations of mass. Where are we going? We won't arrive for billions of years, but our galaxy is on a collision course with something, drawn by invisible forces across the cosmos. Vast regions of space contain almost nothing. The universe isn't evenly distributed. Galaxies cluster along filaments, forming a cosmic web. Between them, voids. Some voids span hundreds of millions of light years. They're not completely empty, but nearly so, maybe 1 or 2 galaxies where there should be thousands. Why so empty? Gravity should fill them somewhat, but they remain stubbornly vacant. Do they tell us something about dark energy, about the early universe? Are they just statistical flukes or signs of physics we don't understand? Voids challenge our models of structure formation. They're the universe's empty spaces, but their emptiness might hide important secrets.
we don't know how everything ends. Current observations suggest the universe will expand forever, eventually becoming cold and dark. Stars will burn out, black holes will evaporate, even protons might decay, leaving only photons and maybe dark matter. This heat death would be the ultimate end, a universe of maximum entropy where nothing interesting can ever happen again. But uncertainties remain. If dark energy changes, the expansion could reverse, leading to a big crunch. Or dark energy might strengthen, tearing apart galaxies, stars, and even atoms in a big rip. Some theories propose cycles, universes that bounce from Big Bang to Big Crunch to Big Bang again, eternally. The fate of everything rests on details we don't yet know. Will there be an end, or is existence eternal? Will the cosmos fade to black or end in fire? Something made the universe expand faster than light. In the first fraction of a second, the universe grew exponentially. A region smaller than an atom expanded to larger than a galaxy. This explains why the universe is so uniform. Distant regions that should never have been in contact look nearly identical. But what drove inflation? A new field we've never detected? An artifact of quantum gravity? Something else entirely? And why did it stop? If inflation started, why didn't it continue forever? The theory works beautifully. Predictions match observations, but the mechanism remains mysterious.
We don't know how chemistry became biology. Life on Earth began at least 3.5 billion years ago. But how did non-living molecules organize into something that could reproduce and evolve? We can create amino acids and other building blocks in the lab, but creating a living cell from scratch? We're nowhere close. Did life begin in tide pools, energized by lightning? In deep-sea vents, fed by Earth's heat? In clay, using mineral surfaces as templates? Did the key molecules arrive from space on comets and meteorites? Each idea has support, none proven. The gulf between organic chemistry and the simplest living cell is vast, and we don't know how it was crossed. Did life begin in water or on land? Most scientists assume life began in water. Oceans are stable, protective, filled with dissolved minerals. Hydrothermal vents seem ideal. But water also dilutes. Chemical reactions need concentration. Some researchers argue life started on land, in shallow pools that evaporated and concentrated organic molecules. Wet-dry cycles might have driven the formation of membranes and polymers. Volcanic hot springs provide energy and chemicals. We're not sure. The answer is lost in time, in rocks transformed beyond recognition. How did the first cell form? Modern cells are staggeringly complex. Membranes, proteins, DNA, metabolic networks. But the first cell must have been simpler. How simple? We don't know. Maybe early cells were just fatty bubbles with self-replicating RNA inside. Maybe they had primitive metabolism, extracting energy from chemical gradients. The jump from chemicals to encapsulated, self-replicating system is immense. It might be the hardest step in the origin of life. Once the first cell existed, evolution could begin. But that first cell remains a mystery.
In the small town of Taos, New Mexico, something strange has been happening for decades. A low, persistent hum. Not everyone can hear it. Only about 2% of the population. But for those who do, it's maddening. It's described as a distant diesel engine idling, a low-frequency drone that never stops. Some hear it indoors, others outdoors. It's been investigated by scientists, acoustic engineers, even government agencies. And they've found nothing. No source, no explanation.
The hum has been recorded in other places too. Bristol in England, Bondi in Australia. Wherever it appears, it defies detection. Some suggest it's tinnitus, a trick of the inner ear. But multiple people in the same location hearing the same sound? That's harder to explain. Others propose ultra-low frequency waves, perhaps from industrial equipment or natural geological processes. But measurements come up empty. The Tao's hum remains, a sound with no source, a mystery wrapped in vibration. For centuries, sailors told stories of walls of water rising from calm seas, waves towering 20, 30, even 100 feet high, appearing without warning and vanishing just as quickly. Scientists dismissed them as myth, exaggeration. The sea doesn't work that way. Until 1995. That year, an oil platform in the North Sea recorded a wave 84 feet high. A single, monstrous swell that appeared out of nowhere. Since then, dozens more have been documented. Rogue waves are real, but how they form is still debated. Normal waves are predictable, shaped by wind and currents. Rogue waves seem to violate those patterns. They're too tall, too sudden, too powerful. Some think they're caused by wave interference, multiple waves combining at just the right moment to create a giant. Others suggest underwater earthquakes or sudden shifts in ocean currents. But no model predicts them reliably. Ships still sink, platforms still get damaged, and the ocean still hides the mechanism behind these liquid mountains. Full power. Here's something that shouldn't work, but does. Give someone a sugar pill. Tell them it's medicine. And sometimes they get better. Not just a little, sometimes dramatically. Pain fades. Depression lifts. Even symptoms of Parkinson's disease can temporarily improve. This is the placebo effect, and it's far stranger than most people realize. Because here's the twist: it can work even when people know they're taking a placebo. Studies have shown that patients told they're receiving fake pills still experience real benefits. Somehow, the ritual of treatment, the expectation, the belief, triggers actual physiological changes. The brain releases natural painkillers, immune responses shift, neurotransmitters rebalance. But why? And why do some people respond powerfully while others don't? We know the effect is real. Brain scans confirm it. But the mechanism, the bridge between mind and body that makes belief into biology, remains mysterious.
You walk into a room you've never been in before, and suddenly, impossibly, it feels familiar. You know what's about to happen next, even though you don't. This is déjà vu, and almost everyone has experienced it. The sensation is so vivid, so convincing, that for a moment, reality feels doubled, like you're living the same moment twice. Scientists have theories. Maybe it's a glitch in memory processing, where the brain accidentally labels a new experience as a memory. Maybe it's a timing error, where one hemisphere perceives something slightly before the other, creating the illusion of repetition. Some suggest it happens when a current scene resembles a forgotten past experience so closely that the brain confuses them. But none of these fully explain the intensity, the certainty, the eerie feeling that time itself has folded. Déjà vu happens to nearly everyone, yet predicting when or why remains impossible. It's a reminder that perception itself is fragile, that the brain sometimes creates experiences we can't quite trust. In 1997,
Underwater microphones in the Pacific Ocean picked up a sound. It was loud, louder than any known biological source, louder than a blue whale, louder than any ship or submarine. They called it the bloop. It was an ultra-low frequency sound, rising rapidly in pitch over about a minute, then silence. For years, people speculated. Was it a creature? Something massive? Unknown? Lurking in the deep? Eventually, scientists determined it was most likely an icequake, the sound of a massive iceberg fracturing and calving. But here's what's strange. The bloop wasn't the only one. The ocean is filled with unidentified sounds. Upsweep, Julia, slow down. Some have been explained, others haven't. The deep ocean is the least explored place on Earth. We know more about the surface of Mars than the bottom of our own seas. What else is down there making sounds we can't identify? Watch someone yawn and you might yawn too. See someone in pain and you wince. This happens because of mirror neurons, brain cells that fire both when you perform an action and when you watch someone else perform it. They're thought to be the foundation of empathy, imitation, even language. But here's the mystery. We don't fully understand how they work or why they exist. Mirror neurons blur the line between self and other. Your brain reacts to someone else's experience as if it were your own. This is powerful. It's how babies learn, how cultures spread behaviors, how we connect. But it raises questions. If your brain mirrors others so automatically, where does your sense of self come from? How do you distinguish your actions from theirs? And why do some people have stronger mirroring responses than others? Mirror neurons are a window into empathy, but the full picture of how they shape consciousness remains unclear. In certain forests, on certain nights, thousands of fireflies flash in perfect unison, not almost together, perfectly, like a single organism breathing light. This happens without a leader, without a signal. Each firefly adjusts its rhythm based on the flashes around it, and somehow they all lock into sync. It's called spontaneous synchronization, and it happens across nature. Pendulums on the same wall will sync their swings. Heart cells in a dish will beat together. But why? The math behind it is called coupled oscillation. Systems that interact naturally fall into rhythm, but that describes what happens, not why nature favors it. Synchronized fireflies serve no obvious survival purpose, yet evolution kept the behavior. It's beautiful, mysterious, a reminder that nature has patterns we're still learning to see.
The universe is old. 13.8 billion years. There are hundreds of billions of galaxies, each with hundreds of billions of stars. Planets are common. Organic molecules are everywhere. The ingredients for life seem abundant. So where is everyone? This is the Fermi paradox. If life is common, if intelligence can evolve, if technology can spread, then the galaxy should be teeming with civilizations. We should see evidence, signals, probes, megastructures. Instead, silence. Maybe life is rarer than we think. Maybe intelligence is a fluke. Maybe civilizations destroy themselves before they spread. Or maybe they're out there and we just don't recognize the signs. The paradox remains, a question mark hanging over our place in the cosmos. Every night, you surrender consciousness. You lie down, close your eyes, and become vulnerable for hours. In evolutionary terms, this is dangerous. Predators hunt, resources go ungathered, time is lost. Yet every animal sleeps in some form. That suggests it's essential. But essential for what? Sleep seems to help memory. It clears waste from the brain. It regulates mood and strengthens the immune system.
But no single explanation accounts for why we need to be unconscious. Why can't these processes happen while awake? Different animals sleep in wildly different ways. Dolphins sleep with half their brain. Some birds sleep mid-flight. Some creatures need almost no sleep at all. What we know is that without sleep, minds and bodies break down quickly. But why we spend a third of our lives doing it remains one of biology's greatest puzzles. There's a book, written in the 15th century, filled with illustrations of strange plants, astronomical diagrams, and human figures. But here's the thing, no one can read it. The text is written in an unknown script. No known language matches it. Cryptographers, linguists, even AI have tried to decode it. All have failed. Some think it's an elaborate hoax, a meaningless jumble designed to look meaningful. Others believe it's a lost language, or a cipher so complex that the key has been lost. The illustrations suggest knowledge of botany, astronomy, biology, but the plants don't match any known species. The astronomical charts don't align with any tradition. The Voynich manuscript sits in Yale's library, a book that refuses to give up its secrets. Most lightning is straightforward. A bolt, a flash, a crack of thunder. But occasionally, people report something stranger. A glowing ball of light, orange, white, or blue, floating silently through the air, drifting through walls, lasting seconds before vanishing or exploding. For centuries, ball lightning was dismissed as myth, an optical illusion. But in recent years, it's been photographed, even recorded on video. It's real, but no one knows what it is. Some theories suggest it's plasma trapped by electromagnetic fields. Others propose vaporized silicon, glowing after a lightning strike. Some imagine chemical reactions sparked in midair, but none fit all the reports. Ball lightning behaves like nothing else in physics, passing through solid objects, defying explanation. It remains one of nature's strangest and most elusive phenomena. You see someone yawn, and suddenly, you yawn, too. You might even yawn just reading this. Contagious yawning happens across cultures, across ages, even across species. Dogs catch yawns from humans. But why? Some think it's tied to empathy. The more empathetic you are, the more likely you are to catch a yawn. Others suggest it's a social bonding mechanism, a way to synchronize groups. But yawning also happens when you're tired, bored, or need more oxygen. So which is the cause and which is the effect? We know mirror neurons play a role, but that just pushes the question back. Why should watching someone else's involuntary action trigger your own? Contagious yawning is so common we barely notice it, but its origins remain a quiet mystery. In 1977, a radio telescope in Ohio detected something extraordinary: a strong, narrow-band signal from space, lasting 72 seconds, coming from the direction of the constellation Sagittarius. It was so unusual, so clearly artificial-looking, that the astronomer who saw it wrote "wow" in the margin. The signal has never repeated. For decades, scientists have debated its origin. Was it a natural astronomical event? A satellite? Or something else? The frequency matched a band that hydrogen emits, a frequency many think intelligent civilizations might use to communicate. But no follow-up observations have found anything. The wow signal remains, a single, tantalizing whisper from the cosmos, unexplained. People who lose a limb often still feel it. They feel itching, pain, movement, even though the arm or leg is gone. This is phantom limb sensation. And it's not imagination, it's neurological.
The brain has a map of the body. When a limb is lost, that map doesn't update. The neurons that once received signals from the missing limb still fire. The brain interprets this as sensation from a limb that no longer exists. But here's what's strange. Sometimes phantom limbs can move. People report clenching a phantom fist or wiggling phantom toes. And sometimes mirrors can help. By reflecting the remaining limb, the brain is tricked into seeing the missing one, and pain can decrease. This works, but we don't fully understand why. Phantom limbs reveal how much of perception happens in the brain, not the body.
Off the coast of Bimini in the Bahamas lies a formation of limestone blocks. They're arranged in what looks like a road or wall, stretching for half a mile underwater. Some believe it's evidence of a lost civilization, perhaps even Atlantis. Scientists, however, think it's natural. The blocks are likely beach rock, limestone formed by natural processes and fractured by geological activity. But the arrangement is unusually regular, almost too regular. And the debate continues. Is it an ancient construction or a trick of geology? The Bimini Road remains a curiosity, a formation that looks human-made, but might not be. Every day, millions of people undergo surgery. They're given anesthesia and consciousness vanishes. No pain, no awareness, just a blank gap in time. Then they wake up. The surgery's over. This is routine, safe, ordinary. But here's the unsettling part. We don't fully understand how anesthesia works. We know which drugs turn off consciousness. We know they affect neurons and neurotransmitters. But why consciousness disappears, where it goes, and how it returns remains unclear. Some anesthetics seem to disrupt communication between brain regions. Others may affect the brain's ability to integrate information. But the exact mechanism, the switch that turns awareness off and on, is still debated. Anesthesia is a mystery we use every single day. In 1908, something exploded over Siberia. The blast flattened 80 million trees across 800 square miles. Witnesses hundreds of miles away saw a fireball, felt the shockwave, but no crater was ever found. The most accepted explanation is that a meteor exploded in the atmosphere, releasing energy equivalent to 10 to 15 megatons of TNT. But without a crater or significant debris, the mystery lingers. Was it a comet? An asteroid? Something else? The Tunguska event remains the largest impact event in recorded history, and we still don't have all the answers. Everyone's fingerprints are unique, even identical twins. They form in the womb, shaped by random variations in pressure and movement. But why do we have them at all? The common answer is grip. Fingerprints help us hold on to things, but experiments have shown that smooth fingers might actually grip better in some cases. Another theory is that fingerprints improve our sense of touch, amplifying vibrations as we run our fingers over surfaces. Or maybe they help channel away water, keeping our grip dry. The truth is, we're not entirely sure. Fingerprints are so familiar, so ordinary, that we forget they're a biological puzzle. Viruses are strange. They're not quite alive, yet not quite dead. They can't reproduce on their own. They need to hijack living cells. But they evolve, they adapt. They've shaped the history of life on Earth. So where did they come from? Some scientists think viruses are ancient relics from before cells evolved, fragments of RNA from the early Earth that learned to copy themselves. Others believe they started as pieces of genetic material that escaped from cells and became parasitic.
A third idea suggests they were once living organisms that simplified over time, shedding everything except the bare minimum needed to survive. The truth might be all of these. Viruses may have multiple origins. What's clear is that they're ancient, and they've been with us, influencing evolution, transferring genes between species for billions of years. Viruses blur the line between living and non-living, and their beginnings remain one of biology's deepest mysteries. You know ice is slippery. You felt it. But have you ever wondered why? For over a century, the standard explanation was pressure melting. The pressure from your foot or a skate melts a thin layer of ice, creating a film of water you slide on. But experiments showed this doesn't work at very cold temperatures. Pressure alone can't melt ice at -30 degrees, yet ice is still slippery. Another theory suggests friction creates heat, melting the surface, but this also doesn't fully explain it. Recent research points to something stranger. Ice surfaces have a naturally disordered layer of molecules, almost liquid-like, even without pressure or friction. But why this layer exists and how it behaves is still being studied. Ice is everywhere, familiar, ordinary, and we're still figuring out why it makes us slip.
Cats purr when they're content, curled in your lap, eyes closed, vibrating softly. But they also purr when they're injured, when they're giving birth, when they're dying. So purring isn't just happiness, it's something else. The sound comes from rapid vibration of muscles in the larynx, about 25 to 150 vibrations per second. Some researchers believe purring has healing properties. The frequency range may promote bone growth and tissue repair. This could explain why cats purr when injured. They're self-soothing, self-healing. But we don't know for sure. Purring might also be communication, a way to signal to other cats or to humans. Cats have lived alongside us for thousands of years, yet the simple, familiar sound remains partly mysterious. In Minnesota, there's a waterfall called Devil's Kettle. The Brule River splits in two. Half cascades down normally, the other half disappears into a hole in the rock. For decades, no one knew where that water went. People dropped dye into it, ping pong balls, GPS trackers. Nothing ever emerged downstream. The water just vanished. Recently, scientists measured the flow above and below the falls. The volume matched. Their conclusion: the water rejoins the river through an underground channel we can't see. Mystery solved, right? Except no one has actually found that channel. The path the water takes remains unmapped. Devil's Kettle is less mysterious than it once was, but it still holds secrets. You wake from a vivid dream. Colors, emotions, entire storylines. You reach for your phone to write it down, and by the time you unlock the screen, it's gone. Dreams vanish faster than any other memory. Why? Some scientists think it's because the brain chemicals that form memories, like norepinephrine, are suppressed during REM sleep. Others suggest dreams aren't meant to be remembered. They're processing, rehearsal, emotional regulation, not storage. But then why do some dreams stick? Why do nightmares linger? The mechanism that decides which dreams we keep and which we lose is still unclear. Dreams are nightly journeys, and most of them dissolve the moment we open our eyes.
In August 1994, gelatinous blobs rained down on the town of Oakville, Washington. They were translucent, sticky, and they covered everything. People who touched them got sick. Nausea, dizziness, flu-like symptoms. A local hospital ran tests. The blobs contained human white blood cells. But how? Why? Some speculated they were waste from an airplane. Others thought they might be jellyfish, evaporated and carried by storms. The military denied conducting any experiments in the area. No definitive explanation was ever found. The Oakville blobs remain an unsolved event, a rain of biological material that shouldn't have happened. Here's a strange question. If you have two containers of water, one hot and one cold, and you put them both in the freezer, which freezes first? Obviously the cold one, right? Not always. Sometimes hot water freezes faster than cold water. This is called the Mpemba effect, named after a Tanzanian student who observed it in the 1960s. It sounds impossible. Hot water has to cool down first. It should always take longer. But experiments confirm it happens. Not every time, but often enough to be real. Why? No one's entirely sure. Evaporation might play a role, removing mass from the hot water. Convection currents might matter. Dissolved gases might affect freezing rates. But no single explanation covers all cases. The Mpemba effect is a reminder that even simple things like freezing water can surprise us. Tears protect your eyes. They wash away irritants. But humans also cry when they're sad, when they're happy, when they're overwhelmed. No other animal does this. Why? One theory is that tears are a social signal. They show vulnerability, drawing empathy and support from others. Another is that crying releases stress hormones, literally flushing emotional chemicals from the body. Some think tears evolved to strengthen social bonds, making emotions visible. But none of these fully explain why we cry from joy, or why some people cry easily while others rarely do. Emotional tears are uniquely human, and their purpose remains one of psychology's gentle mysteries. In Death Valley, there's a dry lake bed called Racetrack Playa. Scattered across it are large rocks. Some weigh hundreds of pounds. And they move. Behind each rock is a trail in the mud showing it has slid across the ground, sometimes for hundreds of feet. But no one ever saw them move. For decades, this was a complete mystery. Then, in 2014, scientists finally caught them in the act. It happens in winter. Thin ice forms overnight. In the morning, wind pushes the ice sheets, which push the rocks. Mystery solved. But it took nearly a century, and the process is so rare, so specific, that it still feels almost magical. About 10% of people are left-handed. This has been consistent across cultures and throughout history. But here's the puzzle. Being left-handed comes with disadvantages. In a right-handed world, tools, weapons, and social norms favor the right hand. Evolutionary pressure should have eliminated left-handedness, yet it persists. One theory is that left-handedness offers advantages in combat. In a fight, an unexpected left hook can catch opponents off guard. Others suggest it's maintained by balancing selection, where genetic diversity is beneficial overall. Some think it's simply a byproduct of brain lateralization, the way the brain divides tasks between hemispheres. Whatever the reason, left-handedness has survived for millennia, a persistent quirk of human biology.
So there they are, 100 mysteries. 100 questions where the answer is simply, we don't know. Some of these will be solved in your lifetime. Scientists are working on them right now, designing experiments, building telescopes, formulating theories. Others might take centuries. Our descendants might look back and wonder how we didn't see the obvious answer. And some might never be solved. They might be the permanent mysteries, the questions that define the boundary of knowable reality. But here's what's beautiful. Not knowing doesn't diminish these mysteries. It makes them more wonderful. Every unanswered question is an invitation. Every mystery is a doorway. Every unknown is an adventure waiting to happen. Think about what we've covered tonight, from the birth of the universe to the nature of consciousness, from dark matter to dreams, from black holes to bird migration. The universe is stranger, deeper, and more mysterious than we ever imagined. And we're privileged to live in an age where we can explore these mysteries, where we can push against the boundaries of knowledge, and sometimes, just sometimes, push them back a little. So as you drift off tonight, let these mysteries carry you. They don't need answers. They only need to be wondered about. Because wonder itself might be the greatest mystery of all. Why should matter organize itself into patterns that can contemplate their own existence? Why should the universe create beings capable of asking why? We don't know. And maybe that's perfect. Sleep well, fellow mystery. Sleep well knowing that the universe is full of questions, full of unknowns, full of wonders still waiting to be discovered. And you're part of that mystery, made of star stuff that somehow learned to wonder about stars. Good night.